Welcome to Maths with EJD. So we talk about eigenvalues and eigenvectors of population models in this situation, talking about practical application of eigenvalues and eigenvectors. We've seen a lot of applications in principal component analysis and data science, vibration analysis and mechanical engineering, image compression, which involves singular vector decomposition. We've talked about its application in stability analysis and differential equations, and so many more. So, I mean, for now, I use this to bring it to a close but there are still a lot more applications of eigenvalues and eigenvectors. So let's see how this looks like. Okay. Um, Eigenvalues and eigenvectors play a crucial role, play a crucial role in Leslie matrix models. No, we're talking about population models. Leslie matrix models are some kind of age-structured population models. So in Leslie matrix models, which are widely used in age-structured population modeling. Okay, these models help predict long-term population dynamics, such as growth rate and stable age distribution. Hey, with that said, let's take an example of a Leslie matrix model. So consider a population, it's age structured, right? A population divided into three age groups, namely juveniles, call that J. Then you have adults, call that A. And then you have seniors, and call that S. So the transition matrix, so here we talk about transition matrix again, like in the case of page ranking, the transition matrix L, known as the Leslie matrix. So the Leslie matrix is the transition matrix. Leslie matrix represents birth rates. It represents birth rates and survival rates, birth rates and survival rates. So imagine L is equal to um, 0 to 1.5, then 0 0.5, 0, 0, and then you have 0, 0 0.6, 0, like this. So where first row, first row is first row shows us the fertility rates, and fertility rates can be defined as juveniles per adult and senior, juveniles per adult and senior. So how many juveniles does an adult or a senior have per adult and senior? Okay. Then you have the sub-diagonal row. So the sub-diagonal row, or say sub-diagonal, right? Sub-diagonal. So that means when we say sub-diagonal, that means everything below this diagonal. So that's talking about these ones. So these are the sub-diagonal. So um sub-diagonal actually talk about survival rates. They are survival rates. So that's juveniles to adults, the rate at which juvenile become adults. That's the first one, which is 0.5. So there's a 50% chance that the juvenile become adults. And adults to seniors, adults to seniors. So the rate at which adults become seniors, and that is at 0.6, which is another 60, which is 60%. Then we have the zeros. So all the zeros also have their significance. So the zeros means no backward transition, no backward transition. Okay, no backward transition. That is, seniors don't go back to juvenile. Seniors don't become juveniles. So if you want to use this for an SIR model, so we may be able to we may be able to write to not have those errors, because somebody who is sick can go back to being vulnerable, to being susceptible. So adults don't become juveniles. Okay, so that goes. Um, so let's move on to something else. If the initial, if the initial population vector, if the initial population vector is P naught, okay, which is equal to 100, 80, 50, meaning we have 100 juveniles, you have 80 adults, and you have 50 seniors, okay? Then the population at the next step, the population at the next step is P1. That is P1 equals LP naught. So, I mean, we can compute this because we have all the information. So, I mean, let me try to undertake this if it's not going to take too much time. 0 to 1.5, 0 0.500, and then 0.60 against P naught, which is 100, 80, 50, 100, 80, 50. So it's just going to be 1. So we have more like, because we have 3 rows, we write that 3 times. So let's see. Okay, let's move to this. So we have 100, 80, 50, right? 100, 80, 50, 100, 80, 50, then another 100, 80, and 50. So we've done this a lot. So we can put this over. So 0 to, the first one is 0 to 1.5. Then the next is 0 0.500, 0 0.500, and the last one is 0 0.60. So this is our P, this will be the population in the next generation. Okay, at the next time step, maybe 1 year after or whatever time step we are taking. So the population at the next step is going to be this. So we have P1 to be equal to, so if looking at the first one, okay, we can even move on to the front like this. So this is 0 already. So the first one we have 160 plus 15 times 5, that's 75, I believe. Okay. Then the next one, 0, 0, easy. So we have 50 again. Then next, 0, 0, 80 times. This is just 8 times 6, and that is 48. Okay. So at the next generation, P1 is going to, the population would now be 160 plus 75. Okay. 160 plus 75. So, yeah. So that is 5, 3. So that'll be 235, and then 50, and then 48. So it means that at the next time step, maybe the following year, if that's what we are considering, we are going to have 235 juveniles, and we are going to have 235 juveniles, right? We're going to have 50 adults, and then we're going to have 48 seniors. So that can go, and we can keep going on like that. So if we want to have the next time step again, so next time step is going to be P2 equals LP1. and then we can keep going like that. Okay, so that can keep going. Now, having said that, so let's also take some steps to get back at, well, talking about the application of eigenvalues and eigenvectors. So let's go for step one. Step one, we find the dominant eigenvalue. So there have been cases where we have to find the dominant eigenvalue. I think the first case in this playlist is where we had to look for the dominant eigenvalue for the power method, I think. I'm not sure. I think that was it, right? So the eigenvalues of L are found. So that's for the Leslie matrix. They are found by solving, of course, we all know how to find eigenvalues, by solving the debt of L minus lambda I, where the lambdas are the eigenvalues, equals 0. So in that case now, we simply have the determinant of, minus, the L is 0 to 1.5. 0 to 1.5, we have 0.500, and then we have 0.60 minus lambda. So this is a 3 by 3 matrix now. So we have lambda 0, 0, 0 lambda 0, and 0, 0 lambda. Okay, that's how that's going to be. And all of this is equal to 0. So from here, we're going to get the characteristic equation. So next we have 0 minus lambda. So we have minus lambda. Okay, we have minus lambda. 2 minus 0 is 2. 1.5 minus 0 is 1.5. So we have 0.5 minus 0, that's 0.5. 0 minus lambda, that's minus lambda. Then we have, this is 0, right? So 0 minus 0, another 0. So we have 0 minus 0 again, 0. 0.6 minus 0, that is 0.6. 0.6. And then we have 0 minus lambda, another minus lambda. And all of this is simply equal to 0. So we can find the determinant now. And I have a whole playlist on matrices where you can understand the idea of determinants and all of that. So you can refer to that. Okay, so now to get the determinant, right, we have to say this is plus minus plus, meaning that the first one we have plus into minus lambda into, so cross out its row and its column. So we have minus lambda 0, 0.6 minus lambda. Okay. So with that done, we can erase this again. So we go for the next one. We have minus 2 now into cross the column it belongs to and cross the row. So we have 0.50, 0 minus lambda. That's talking about 0.500 0 minus lambda. Then lastly, we can also erase that, right? So we have plus 1.5. So we have plus 1.5 into cross the column, cross the row, and we have 0.5 minus lambda, then 0, 0.6. Okay, and all of this is equal to 0. All right, so we can restore to factory setting if you like. So we can go on with this now. So this is minus lambda into, yeah, we are taking determinants, right? So that's minus lambda times minus lambda, that's lambda squared minus 0.6 times 0.6 minus 0, that's simply 0. Then minus 2 into minus 0.5 times minus lambda, that's minus 0.5 lambda. Then minus 0, that's 0 times 0, plus 1.5 into 0.5 times 0.6, that's 30, right? Two decimal places, that's 0.30. Okay, I believe that. Then so 0 minus lambda is also minus 0. So all of this is equal to 0. So that's how we proceed. So we have minus lambda into lambda squared minus 2 into minus 0.5 lambda plus 1.5 into 0.30, and that is equal to 0. So we have minus lambda cube plus 2 times 0.5 is 1. That's lambda. Then 1.5 times 3, that's 45, right? That's 1. 1.5 times 0.3. So we have 15 times 3 is 45, and we need two decimal places. So that is going to be 0.4. Is it 0? 15 times 3. Okay, that's 1.5 times 10 raised to power minus 1. 0.3 times 10 raised to power minus 1. That's 45 times 10 raised to power minus 2. Yeah, that's 0.45. 0.45. That's equal to 0. So we have lambda cube, okay, lambda cube. If you divide through by minus 1 or multiply through by minus 1, we have lambda cube minus lambda, all right, minus 0.45 equals 0. So this is what we call the characteristic equation, which we solve to get the eigenvalues, okay? So this is the characteristic equation. Without the equality side, it becomes a characteristic polynomial. So I mean, so I don't want to go through any stress solving that, so I'll just jump straight to the answer. So the results of the results the results for solving the characteristic equation, will give the eigenvalues as follows. Okay, so we have lambda 1 is equal to 1.1759. If I take it to 5 decimal places, I mean to 4 decimal places, so that's lambda 1. Then we have lambda 2, which is equal to minus 0.58 minus 0.5879 plus 0.1924i. Then we have lambda 3, which is minus 0.5879 minus 0.1924i. Okay, so these are the three eigenvalues, right? Are the three eigenvalues. But I mean, for the sake of, since we're talking about population, the most important eigenvalue is the dominant one. That's the biggest of them, and that is this one now. Okay, so the biggest eigenvalue is lambda 1 equals 1.1759. And what is the implication of that? That actually has some meaning as far as the population is concerned. What that simply means is that the dominant eigenvalue, the dominant eigenvalue, which is lambda 1, which is equal to 1.1759, represents this. So because it's dominant now, it has the biggest determination, it determines the population the most. So represents the long-term growth rate, the long-term growth rate of the population, to represent the long-term growth rate of the population. Okay, so with that done, we can go to step 2 now. Step 2, we have only found eigenvalues. The eigenvectors also have an impact on the population. So we have to find the corresponding eigenvector to the dominant eigenvalue. We don't need the other ones because the dominant eigenvalue tells us all the story we need. So in that case now, we need to solve L minus lambda I V1 now, or let's just say V, which corresponds, or let's say V1, right, which corresponds with the dominant eigenvalue. So in that case, we know the dominant eigenvalue is 1.1759. So in that case, we just have L minus 1.1759 I, okay, Vi equals 0. So in that case, we are simply saying that we have so we are going to have 0 to 1.5, 0.500, 0.60 minus this is 1.1759, 0, then 0, 1.1759, 0, then this is 0, 1.1759, okay, 1.1759. Okay, so we have to shrink this. So all of this now multiplied by V1, that's V1x and V1y, and that is equal to 0, 0. So we can do all this. Well, at least I can try to tidy up. So now we just have minus 1.1759 to 1.5. Then this is 0 0.5 minus 1.1759, 0. Then we have 0, 0 0.6 minus 1.17, 1 minus 1.1759. Okay. We have one minus 1.1759. Okay. So with this now, so this is multiplied by V1x and V1y. All of this is equal to 0. So, I mean, I won't stress, I won't, okay, we have three things here, right? So it should be 3. So this should be V1x, V1x, V1y, and V1z. So same here. So this should be V1x, V1y, and V1z. And we can do all of that. At the end of the day, right, we are going to get these eigenvalues. So if we solve all this now, we are going to get at the, so, okay, solving this, we have, solving this, we are going to have V1 to be equal to 4.608, or let's say 4.6090, then 1.9598, and then 1. And since we are talking about population, okay, so we have 1, right? So since we are concerned with population growth, we normalize V1 such that V1x plus V1y plus V1z is equal to 1. And the only way to do that is to say now that V1 normalized is going to be 1 all over, all those things we have there. That's 4.6090 plus 1.9598 plus 1 into all what we have. That's 4.6090, then 1.9598, then 1. So all this. So at the end of the day, V1 normalized. That means we're going to divide each one by the sum, by the total sum here. At the end of the day, all of that is going to give us the following. So we just have 0 0.60 0.6090, and here we have 0.2589, and we have 0.1321. Okay, we have all this. So that's the normalized thing. So this now helps us to talk about how the population is going to grow afterwards. So now that we have normalized that, so we have normalized the eigenvector, so we can begin to make comments about the fate of the population afterwards. So so this eigenvector, V1 norm represents the stable age distribution. So that means after a very long time, the stable age distribution that talks about the ratios of juveniles, adults, and seniors. Okay, all of this in the long run. That's what the stable age distribution is in the long run. Okay, so now what's the interpretation of this whole thing now? Interpretation. So first of all, Number one, we have the growth rate. The growth rate. Because it's the growth rate is bigger than one, right? So it means the growth is going to keep increasing. So since the dominant eigenvalue one is 1.1759, the population, okay, grows by 17.59%. Okay, that's so it means you have the population preserved and you have extra. That's what that means. 17, the population grows by 17.59% per time step. So each year the population grows by 17.59%. That's the first part. Number two, we talk about the stable distribution. Stable distribution. So in the long run, the population is going to have a stable kind of distribution, and that is determined by the eigenvector. So you see, this is the growth rate is determined by the eigenvalue, while the stable distribution is determined by the eigenvector. So you can see their impact on the population in the long run. So, so what this means is that over time, the population stabilizes. The population stabilizes in the ratio in the ratio. Yeah, what's the ratio now? It's going to be dependent on this now. That's 60.9%, right? 60, the ratio is 60.90% to ratio. The next one is 25.89%. So that's 25.89% to ratio 13.21, I believe. 13.21%. So that, yeah, everything goes to 100, 13.21%. So it means that in the long run, you are going to have 60.9% of juveniles in each generation. So it stabilizes, and you have 25.89% of adults, and you're going to have 13.21% of seniors. That's what all of this implies. Okay. So in essence, we are saying that the eigenvalues, thus, the eigenvalues determine the eigenvalues determine population growth trends. Okay. While eigenvectors provide the long-term structure, the long-term structure of the population. Okay, that's what this is saying. So you can see eigenvalues and eigenvectors have a very serious role to play. Now, you may also want to look at the Python implementation of this. So basically you just have this, right? So imagine, so you declare the Leslie matrix, talking about the birth rate, the survival rate, and all of that. So then you compute eigenvalues and eigenvectors, just like you already know. So we can do that in linear algebra. Then the next thing is you now have linear algebra that you can get from NumPy rather. So you get the dominant index, dominant eigenvalue, blah, blah. So you just run this and it gives you all those things I just showed you. So you see 1.1759, that's the dominant eigenvalue. The other ones don't really matter because the dominant eigenvalue takes care of decides the fate of the population in the long run. And you see that the population is at 117%. It means that it's increasing by 17.59%. And then stable age distribution will now be 0.608. That's the proportion now. So that's 60.90% are juveniles, 25.89 are adults, and 13.21% are seniors. So if you look at it like that. So that's how that has been. And It's such an interesting thing to look at. If you have subscribed to the channel, thank you so much for doing that. If you have not, please go ahead and do that because there's still a whole lot to learn. I'm still going to be talking about numerical methods for different things like partial differential equations, bounded problems, and so much more coming under numerical analysis. So if you have not subscribed, please do good to subscribe and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are, and let me know if there's a topic you'd like me to treat or a problem you'd like me to solve. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.